Greetings, AP Chemistry students. Today we're going to transition into the last part of Unit 9, which is Electrochemistry. And I hope to finish this up next Tuesday and Wednesday. And then Thursday and Friday of next week, we'll look over some of the stuff from the AP exam because they're supposed to release your results to me. And so we'll have a little Google Meet then to talk about all that good stuff. But electrochemistry is one of the most important aspects of chemistry to your day-to-day lives because things like cell phones and laptops and all sorts of other things that you depend on as part of modern life would not be possible without electrochemistry. But electrochemistry is the study of redox reactions that occur within electrochemical cells. If y'all remember redox, that's oxidation reduction. Oxidation is losing electrons. Reduction is gaining electrons. And electrochemical cells are devices that separate those parts so that the electrons can move. And a device called a galvanic cell generates an electrical current. And I have two examples of galvanic cells for you. I have this one right here. This one right here is a D cell. And then I have this one right here. This is a size AAA cell. These are commonly called alkaline batteries, but this is technically not a battery. This is a cell. This, on the other hand, is a battery, because if you were to actually open this up, you would find inside of this 6 tiny little cells connected inside of it, because each one of these cells generates 1.5 volts of electrical potential, which we'll talk about. This generates 9 volts, and if you multiply 1.5 by 6, you get 9, and that's how you get the 9 volts. Is there's packaged inside of this little rectangular prism are 6 of these, of a smaller version of those little cells. So that's a little technical difference. Now, there's also what's called an electrolytic cell, and these are ones that they don't generate electricity. These are ones that you apply electricity to and a reaction happens. A rechargeable battery, when it's being recharged, is an electrolytic cell, but there's a lot of other cool applications of these as well. But galvanic cells are devices that convert chemical energy into electrical energy. And there's a redox reaction that takes place, and the substance that's being oxidized transfers its electrons to the substance being reduced. And if you look at how this actually works, the oxidation part, electrons are being lost out of the negative end of this cell, because electrons are negative, and they flow through. And then on the other side, the positive end is connected to the reduction side where the electrons are being gained. And essentially, there are half reactions that are separated by a salt bridge. So you have oxidation taking place in one part, reduction in the other, and they're separated by this device called a salt bridge that will separate the reactions but allow electrical charge to flow. And some terminology that's used with these: the anode is where oxidation occurs, and the cathode is where reduction occurs. And on a galvanic cell, the anode is the negative side of the cell, and the cathode is the positive side. Now, cell potential is also known as the electromotive force, or EMF, which is abbreviated with a capital E. That is the driving force, or what actually pushes the electrons along. And it's measured in volts. So I already mentioned this provides 1.5 volts. This provides 9 volts. The battery in your cell phone provides around 4.2 volts. And technically that's a cell, not a battery in your cell phone. The battery that's in an automobile provides 12 volts. But a volt is a joule of work per coulomb of charge transferred. And a coulomb of charge is essentially the amount of charge contained on a specific number of electrons. Now, all thermodynamically favorable galvanic cells, in other words, these things, they produce a voltage, a reaction happens, they have a positive cell potential, meaning that their change in Gibbs free energy is negative, and their equilibrium constant is greater than 1. So all three of those things play together. And as you might guess, there's a relationship between these things. Specifically, the change in Gibbs free energy equals negative NFE, where E is your cell potential under standard conditions. This is Gibbs free energy under standard conditions. There's a negative sign there. But then F is Faraday's constant. And Faraday's constant is 96,485. That's on your chemistry reference tables. That means there are 96,485 coulombs of charge for every mole of electrons. A coulomb is a unit that's used to measure electrical charge. And N is how many moles of electrons are transferred in the reaction. So you would have to actually analyze the reaction in order to figure out how many moles of electrons are transferred. Today we're going to talk in a little more detail about how a cell, a galvanic cell, or what's commonly known as a battery, actually works. And to do that, I need to define something called standard reduction potential. So a standard reduction potential is all referenced to something called a standard hydrogen electrode, where you have 1 molar in H pluses or acid plus hydrogen gas at 1 atmosphere. That's defined to have a cell potential of 0 volts. And so anything compared to that has a voltage that can be measured higher or lower than 0. Now, standard reduction potentials are cell potential values for a reduction half reaction where any solutions are at 1 molar, any gases are at 1 atmosphere, and your temperature is at 25 degrees Celsius. And the College Board used to provide you on the AP exam with a lovely chart of standard reduction potentials that list a whole bunch of half reactions. They're all written as reduction half reactions. Let's see if I can show you this. Here's a copy of this. They're all written as reduction half reactions, and they give you their cell potentials. And at 0 volts, you have the standard hydrogen electrode. Now, these are all reduction half reactions, and if you remember from our lessons on redox many months ago, learned that you can't have reduction, something gaining electrons, without something being oxidized and losing electrons. So in order to actually make an electrochemical cell, you need to take one of these half reactions and run it in the forward direction, and the other half reaction and run it in the reverse direction. And so when you do that, ultimately your cell potential is going to be the sum of the cell potentials of your two half reactions. So you're just going to add the cell potentials together for both of those. So if we go back to the notes here, one of the half reactions must be reversed. And you also have to multiply the half reactions by some integer values so that when you add them together, your electrons cancel out. Now, if you double a half reaction, it does not change its cell potential. You're just changing the number of electrons that are involved, right? And this shows essentially how a galvanic cell is constructed. You have your solutions of your ions that are 1 molar, you have your solid pieces of metal, and then you have this thing called a salt bridge, which allows the flow of ions back and forth in order to balance charge. And typically the ions involved are ions of potassium nitrate, and the ions will flow into the different beakers in order to balance the charge out, because without the salt bridge, you would be dumping positive ions into one half of this container and negative ions into the other half, and you would build up a whole bunch of charge inside the cell, and it just wouldn't work. So this kind of shows you have your anode where oxidation takes place. Ignore these terms, reducing agent and oxidizing agent. But you have over at your anode is oxidation, where electrons are being lost, and electrons will flow through a wire over to where you have reduction, and electrons are being gained. And since you're dumping electrons into the beaker on the right hand side, then you're going to have positive ions moving through your porous disk this way, and negative ions moving through your porous disk the other direction. Or if you had a salt bridge with potassium nitrate, you would have potassium ions, which are positively charged, moving towards the right side where the electrons are going, and nitrate ions, which are negatively charged, moving the other way. All right, let's look at a few examples. The first one I have, I'm going to talk about what happens inside of a traditional alkaline cell, either a double A or a triple A or a C cell or a D cell. It's all the same chemical reaction. So what I have right here are two reduction half reactions. They're reduction because electrons are on the reactant side. These are gaining electrons as you go. And if you remember the old acronym, oil, rig, oxidation is losing electrons, reduction is gaining electrons. Well, something needs to be oxidized, and so we need to reverse one of these reactions. Now, I also have their cell potentials over here, and you may notice that this one right here is at a negative 1.28 volts. It would probably be helpful if that voltage were positive. So if we take that first reaction and we write it backwards, we would have zinc plus 2 hydroxides makes zinc oxide plus water plus 2 electrons. And if we reverse the reaction, the cell potential changes sign. It becomes a positive 1.28 volts. So we're going to take these two reactions and we're going to add them together. And if we add these reactions together, then our electrons on either side will cancel out. The water on either side will cancel out. And the 2 hydroxides on either side will cancel out. So we end up with zinc plus 2 manganese 4 oxides produce Mn2O3 plus zinc oxide, and our cell potential would be a positive 1.43 volts. And these are typically called 1.5 volt batteries or 1.5 volt cells. And 1.43 is pretty close to 1.5 volts. These are also called alkaline batteries or alkaline cells. Alkaline is a term that means basic, and these have hydroxides in them. There's a paste of potassium hydroxide that acts as both the salt bridge and the source of hydroxides in the reaction. There's also a tiny amount of water that's in there. And what's ingenious about the packaging of a traditional little cell is the zinc also doubles as the outer casing. The outer casing of the cell is actually made of the zinc. And so as the energy is used up in the cell, as the reaction proceeds, the zinc casing is actually depleted to some extent. Now, it starts obviously a lot thicker than it needs to be because it doesn't disappear. And if you've ever had some batteries in your remote control leak, what you're actually leaking out is the potassium hydroxide, the electrolyte that's in there. So it's those white crystals that ooze out of old batteries. Let's take a look at one more example of this. So here I have 2 reduction half reactions. I've got lithium being reduced to make solid lithium and nickel being reduced to make solid nickel. So lithium ions and nickel ions. Now, in order to make this reaction work, I'm going to need to reverse one of them. And a galvanic cell has a positive cell voltage, so when we add the voltages together, we need a positive number. So I'm going to reverse the one of these that is the most negative, so it will become positive. So I'm going to take that first reaction and reverse it, so that we have lithium as a solid being converted to lithium ions plus an electron. And that would be a positive 3.05 volts. Now, to add these two reactions together, the other thing we've got to do is make our electrons cancel, because we've got two electrons there. We've only got one electron here. So we need to take this bottom reaction and double it. Now, that does not affect our cell potential. But when we add these reactions together, we're going to end up with a nickel with a +2 charge plus a lithium as a solid, or actually have two lithiums as a solid, makes solid nickel plus 2 lithium ions. And if we add our cell potentials together, we're going to get a cell potential of 2.80 volts. And if we look at this in action, essentially you would put lithium metal and a lithium electrolyte solution together, and then you would put nickel metal and a nickel electrolyte solution together with nickel ions in it, and you'd have your salt bridge, and then you would generate the cell potential and electrons would flow.